Good morning.
Hi everyone. I'm Barry Smart. I graduated from Robert Gordon University and I've worked at Gyrodata and then subsequently SLB for 28 years. Started in the field, became an operations coordinator, and then I've worked in technical support for the last 18 years.
And I am Ezra North. Went to the University of Texas at Austin. And I've been around for quite a while as well now, 26 years. And started at Gyrodata, and then 3 years ago, we were married into the SLB family. And so it's been 3 good years of that. And certainly, like everyone else, started in the field and then worked my way through all these different roles. And now I'm currently an account manager globally. So this was presented in Galveston and at the SB, the IADC conference just about a month and a half ago. We're going to talk about dynamic gyrocompassing and how it is, driving new efficiency and safety. We'll talk about kind of how it was in the past, the theory of what we've developed, innovated, a little bit on the validation of it, and then we'll talk a little more about discussion points and conclusion. Well, I don't know if you recognize this guy here, but the good old days. So this picture was taken about 25 years ago. That was actually my 15th birthday. And yeah, I mean, I'm smiling here, but the reality is we didn't have GWD when I started. And we did these things called single shots and orientations, and we used methods that were effective, but certainly not efficient. Really nothing efficient about this at all. You'll see there's a mule shoe sub, a stinger, and a UBHO sub, and we really just would run in and out of the hole over and over again and give an orientation, a tool face, inclination azimuth, and then allow the directional driller to do their planning and projections, and on and on and on and on and on. And you never really got any sleep. It was actually quite miserable, to be honest. And coupled with that, you had really an unsafe operation. The wireline unit was required either a slick line or electric line. You're lucky if you had electric line, but often it was just a slick line unit. You can see all of the dangers. You've got high voltage cable, you've got potential for dropped objects. You're on the rig floor. Sometimes you're racking back this gigantic spear point tool in the derrick. And then of course, you're not able to circulate, you're not able to work the pipe. There's a lot of things that are risky in terms of having the BHA in the hole. So as we all know, GWD came along, and now we've removed a lot of the inefficiencies associated with the single shots. And we certainly innovated over the years, as we've talked about, the sensor technology, the ability to actually just incorporate this with the MWD. And now we're in the BHA, and we're taking measurements as needed on demand with the mud pulse or EM systems. But the reality that we faced was we're still not understanding or able to cope very well with the noise, the environmental noise. This is especially offshore. You've got high heave, you've got movement from the seas, currents, winds, everything going on. And the gyro measurement, clearly very, very sensitive measurement. So understanding how we could fix that was really iterative, and we started really without anything. And the early days normal mode, as I have here, was really often unsuccessful. So we did have to have that same wireline unit and everything standing behind it. We had a UBHO on top of the MWD. We were often using single shots to validate, and sometimes we were, quite frankly, run off, replaced by our competitor, and then they would be run off. So we had to get better, and we did. We found an effective way to manage the situation, which Barry will talk a little bit about. But really, the step changes when we came and went from extended mode into this DGC dynamic gyrocompass. Barry?
Yeah, thanks, Ezra. Just to elaborate a little bit more on extended mode. In normal or standard mode, we collect surveys over a 12-second sample period and we do 5 passes. With extended mode, we extend, as the name suggests, that sample period to 90 seconds. It doesn't do any filtering or correcting. It's just basically a longer sample period where we hope the noise cancels itself out over the longer period. It's served us pretty well, but there are really operational compromises involved with extended mode. First of all, when we're using it top hole on floaters, we always need to compensate, which means all of our survey times in the critical path and not swallowed up over the connection. We often need to use survey repeatability to validate our surveys, so check for repeatability over multiple surveys, and typically each repeat survey costs an additional 10 minutes of rig time. It can also lead to hole washout and top hole softer formations. If that doesn't work, we're then on to secondary procedures, which can include putting weight on bit and the dangers that come with that, blocked nozzles, getting stuck completely. And then if that fails, we then go on to potentially rotating down a single to get the BHA bedded in more to try and get a survey. But if they need directional control at the seabed, we then have to run the wireline gyros that Ezra described in sighting mode. So the solution was dynamic gyrocompass. The principles of it are that the gyroscope needs to be stationary to measure the components of the Earth's rotational field. External motion will contaminate the gyroscope readings. The dynamic gyrocompass method addresses the problem by estimating the motion-induced rotational components and removing them from the gyroscopic measurements. The motion-induced components are estimated using the accelerometers. So we developed a project, and the objectives were really fourfold. The ability to survey over connection with QC passing first time, operate from an inclination range of 0 to 10 degrees, performance equivalent to the extended mode gyro IPM, and also have a sample time of a maximum of 10 minutes. So to break it down, we have the triaxial gyro measurements, which are split into motion-induced components and components of the Earth's rotational rate. We then use the accelerometers to calculate the motion-induced components on the X and Y axis. We don't need the Z axis, top hole near vertical. And then from there, the compensated rates are used to compute the azimuth and or the inertial gyro tool face.
It's basically like noise canceling headphones. You put them on, you don't hear the baby crying on the plane, but you hear the movie you want to watch.
Thanks, Ezra. So on to the concept validation. During initial tests, we didn't feel that we could adequately replicate the motion of a floating vessel in the shop. So we spent some time on several rigs, strapping tools to poles offshore, on deck, on semi-subs. We collected data. We've got an example on the slide that you can see. So we can see the effect of the BHA tool movement in the readings. What you'll notice is that there's a high correlation between the gyro measurements on the top and the accelerometer measurements on the bottom. We're using a continuous mode here, so it allows us to better monitor and track the movement of the BHA. Probably the last thing that's worth mentioning here is that we're measuring a horizontal earth rate of about 7 degrees per hour here, and we're seeing noise levels well in excess of 100 degrees per hour. So the signal to noise ratio is not particularly favorable. So initial test results, we collected data alternating between DGC and extended mode with the tool on deck strapped to a pole, as we mentioned. So the tool underwent a 4-quadrant rotation shot at less than 1 degree inclination. So the DGC results in blue show relative stability, whereas the extended mode surveys are particularly erratic. All of the DGC stations pass QC, while only 6.25% of the extended mode surveys pass QC. The next stage was to get it in hole. So the DGC tool was integrated into a gyro sighting tool on BP Clare Ridge. We collaborated quite a bit with BP on the development of this. The reason being there was a big win for them because they were in a situation where they still needed to use the sightline gyro on all of their top hole operations on Clare Ridge. So on one of those sighting runs on Clare Ridge, we incorporated a DGC tool into the tool string, and basically as we sighted the tool, ran in, located on the UBHO, stayed there for a while, collected a bunch of DGC data, pulled out of hole, realigned on surface as we do with a sighting tool, and the graph shows the comparison between the DGC and the wireline sighting gyro inertial tool face. So we've got really strong correlation. So all of this gives us confidence to take the next step and go to the field. Again, we did this first on BP Clare Ridge. So the DGC was utilized for surveying the top hole in a 2-well batch on Clare Ridge. On the first well, we completed 11 DGC surveys. Because it was the first field deployment, we also, as we started the kickoff, we ran 2 sightline gyros to compare the DGC to the sighting gyro. And as you can see from the table, really strong correlation. So we only completed 2 sighting runs, and between ourselves and BP, we were happy to proceed with the Dynamic Gyrocompass surveys. Once we'd built inclination, we then managed to run a wireline multi-shot and compared that with 5 further DGC surveys. And again, good correlation and good azimuth comparison based on the tolerances, based on the relative uncertainties of both tools. Okay.
Well, it's really been a success. So it's not often that you get to talk about gyros bringing more efficiency. Really, since we innovated GWD and made that big step change, we soon became not heroes anymore, but we're tired of waiting on the gyro, of course. So to be able to go and see our clients, see our partners and say, look, now we can really start getting surveys, as Barry pointed out, on connection, not after, and not using the compensation methods was a big deal. So we actually, this first trial was not even a year ago, it was in June in the North Sea. And as you would imagine, most of the developments, actually the foundation of gyro data was North Sea. The applications there, the needs are certainly at the higher end of the market. And so we did that and we achieved our goals, but clearly we found quickly that there's places that also have challenges on floating rigs, namely West Africa, little country called Guyana. You may have heard of that oil field. So these are all places where you've got really high heave, and it's not appreciated just how much the impact that can be on the operation, namely the gyro. So as you can see here, it's just been really very successful, and I've traveled to a lot of these places and seen the customers. So it's really been an exciting start. So to bring it all to a close, really we spent quite a few years. I don't think we've kind of highlighted that enough, but Gyrodata and now SLB, we've really continued to invest time, engineering resources, and sometimes these things were done without a business case or all the things that modern companies would demand. We just did it because we want to be better. And Adrian and the team started work on this probably at least 5, 6, maybe more years ago. But when it came to fruition, it's been a huge success. And we ticked the boxes. And not only did we tick the boxes, we pushed the limit of the design. It was supposed to be a 10-minute survey, which didn't get the wow factor. Certainly, usually you're making a connection faster than 10 minutes. So the feedback from operations, from technical services to engineering was, we really would like this to be 6 minutes, and that was attained also. So overall, a really big success, and now I'm the lucky one that gets to go pitch this to our customers. Certainly want to acknowledge and thank this group. Thank you, Chad and Tim. Thank you, ISCWSA, past, present, future. And of course, SLB. The fact that we're still bringing these developments to the market, and not only just for SLB, this is something we've shared with all our partners, this technology, as we always have. And then BP really was supportive and allowed us to promote this, and was happy to share the success that they're realizing as well. So thank you for all of that. Just wanted to take a minute. You may have seen this on LinkedIn. Bob, dear friend of mine, Bob founded Gyrodata. Maybe, I don't know if anyone in this room was lucky enough to get to know Bob, but a great person, a visionary. He started Gyrodata around 1980. He completely lived in the market. He studied it. He spent time. He built relationships. He valued every single bit of this industry, and really the founding of Gyrodata, as I alluded to, it came in the North Sea. Also, just the realization that in those days you had to shut in all the production to do a kickoff to drill a new well, and so that's what started it. I asked him one time what his strategy was, and he said, "We just want to be the very best." And he said, in those days, Schlumberger wireline was the gold standard for how things were done. We want to be that good. Gyrodata, Bob and his partners never stopped improving. Every downturn was just another chance to try to advance a little bit more. And most importantly, they really made sure that they never lost their people. They didn't work like on a quarterly basis. They had vision, they had strategy. So cheers, and everyone raise your glass to Bob tonight if you would. He would appreciate that.
Thank you. Carol's got the mic. If you could, if you have any, state your name, affiliation, and
It's still early.
Well, I'm very. I was just wondering what you can see you've got on it. You see dynamic limits. I only expect you can't come close to that project.
I don't know why Barry's trying to take the mic. I'll hand it to him though.
It's standard PC that we use for gyrocompassing. So we've got a delta earth that we use to basically QC. So we use that basically.
All right, yeah. Ahead of schedule, Chad.